Welcome to The Explainer. So today, we're going to look at a machine learning model that honestly thinks a lot like we do, the decision tree. It actually solves really complex problems by playing a game we all know, 20 questions. And we're about to break down exactly how it pulls that off. All right, to get our heads around this, let's start with a kind of fun challenge. Let's say we want to build a model that can look at any location on Earth at any time of year and tell us, can you ski there? Now, on the surface, this sounds pretty simple, right? But it's actually the perfect problem to show us why we need a much smarter approach. So, what makes the skiing challenge so tricky for a computer? Well, it's because you just can't draw one single straight line to separate the ski spots from the no-ski spots on a map. And that right there is what we call a nonlinear problem. I mean, think about it, right? In the northern hemisphere, you're skiing in, say, January. But down in the southern hemisphere, you're hitting the slopes in July. And near the equator, forget about it. So if you were to plot this all out on a graph of latitude versus month, you'd get these totally separate blobs of ski regions. Any simple straight line model would just completely fail. It wouldn't know what to do. So, okay, if a straight line is out, what's the solution? This is where our hero of the day, the decision tree, steps in. See, instead of trying to find one super complex rule to solve everything, it does something we all know how to do. It plays a game of 20 questions. Okay, so the fancy term for this is recursive partitioning. But don't let that scare you. It's a really simple strategy. You just take a big, messy problem, and you split it in two by asking one simple question. Then, you take those two new, smaller chunks, and you do it again. Ask another question, split them again. Over and over and over. All right, so let's see this in action. What's the very first question our ski-finding tree might ask? Well, a really smart opening move would be something like this. Is the latitude greater than 30 degrees north? This immediately helps us narrow things down. And boom, just like that, with one single question, we've basically sliced the world in two. Now, have we solved the whole problem yet? Nope, not even close. But we've made it way, way simpler. This is kind of the greedy logic of a decision tree. It just makes the absolute best split it can see right now, without really worrying about what's going to happen 5 steps down the line. Okay, so what about all those places that answered yes to that first question? Everything in the Northern Hemisphere. Well, now we can ask a follow-up question just for them. How about something like, is the month before March? See, this is that recursive part we were talking about. We're asking new questions inside the regions we just created. And with that second question, we've basically carved out this little box on our map that represents the early winter months up north. And inside that box, the data is now really pure. It's almost all yes, you can ski. So you see, just by asking a series of really simple questions, the tree starts to isolate the different outcomes. This all seems pretty straightforward, but it brings up a huge question, right? How in the world does the tree know which questions to ask? I mean, out of all the thousands of possible questions, how does it pick the one that's going to simplify the problem the most? Well, that's the thing. As Raphael Townshend from Stanford's CS 229 course puts it, at each step, we want to pick the best partition possible. The tree is greedy. At every single fork in the road, it looks for the one question, that one split, that's going to give it the biggest win right now. It's not playing chess thinking 5 moves ahead. It's just making the best possible move it can, right here, right now. So how does it measure what a good split is? It uses something called a loss function. The easiest way to think about it is like a scoring system. A question gets a really high score if it creates new groups that are super pure, meaning pretty much everything inside that new group is the same. Just like that yes, you can ski box we made. But here's the catch. Not all scoring systems are made equal. You could use a simple one, like misclassification loss. It's okay. It can tell you if a split helped or not, but that's about it. It can't really tell the difference between a pretty good split and a great split. Then you have something much smarter, like cross-entropy loss. This one doesn't just care about getting the answer right. It gives you huge bonus points for being really confident about that answer. And that's what pushes the tree to find those splits that create the absolute purest, most confident groups possible. Okay, so decision trees seem awesome, right? They're powerful, they're easy to get your head around. But like any good hero in a story, our decision tree has a fatal flaw. It's a bit of a flawed genius. And honestly, its weakness is a pretty big one. I mean, the pros are fantastic. Decision trees are super easy to explain, they can handle all kinds of data, and they're crazy fast. But
That huge weakness, we call it high variance. And the best way to think about it is like a student who crams for a test just by memorizing every single answer on the practice sheet. Yeah, they might ace that one test, but they haven't actually learned the subject. The tree does the same thing. It basically memorizes the training data, including all its weird little quirks. So the moment it sees a new, slightly different problem, it totally fails. That's called overfitting.
So, how do we fix this overfitting problem? How do we help our flawed genius? Well, here's the brilliant part. We don't try to build one single perfect flawless tree. No way. Instead, we build a team. This whole idea is called ensembling, and it's how we turn our flawed hero into an absolute world-class champion. And the logic here is actually pretty simple. Any single decision tree might be a little unstable, It might make some weird predictions because of the specific data it happened to see. But what if you train lots of different trees on slightly different versions of the data, and then you just average their opinions? All that weirdness, all those individual mistakes, they tend to cancel each other out. It's literally the wisdom of the crowd. One of the most popular ways to pull this off is called bagging. Basically, you take your data and you create a bunch of random little samples of it. Then you train a whole bunch of trees, one on each of those random samples. By creating a whole committee of trees, where each one has a slightly unique perspective on the problem, you drastically reduce that high variance that was giving us so much trouble. And this idea, bagging, is the exact principle behind one of the most famous machine learning algorithms out there, the random forest. It's basically a whole bunch of bagged decision trees, but with one extra little twist of randomness. At every single split, each tree is only allowed to look at a random handful of features. This forces the trees to be even more different from each other, making the team even stronger. Okay, so that's bagging, but there's a totally different approach called boosting. It's really different. Instead of building a whole committee of independent experts all at once, with boosting, you build a team of specialists one after another. So the first tree makes its best guess, then the second tree comes along, and its entire job is to focus on fixing the mistakes that the first tree made. Then the third tree focuses on the mistakes of the second, and on and on. It's like a team that learns from each other's mistakes in a sequence. Okay, so let's put it all together. This is the crucial difference. Bagging, think random forest, is all about reducing variance. It's like asking 1,000 people for their independent opinion, all at once, so any single crazy answer gets drowned out by the average. Boosting, on the other hand, is about reducing bias. It's like building a chain of experts, where each person's job is to correct the specific mistake made by the person right before them, getting closer and closer to the perfect answer with every single step. And that's the whole story. The simple, intuitive, but kind of flawed decision tree doesn't have to go it alone. By becoming a part of a bigger ensemble, a super team like a random forest, or a boosted model like XGBoost, it becomes the backbone of some of the most powerful, most accurate predictive models we have in the world today. It's a really powerful idea, right? That a team of simple models can beat one complex one. And it really leaves you with a final thought. What other huge, complex problems out there could be solved not by searching for one single perfect model, but by building a team of simple ones working together?